There's a particular way of thinking that separates those who truly understand something from those who merely believe they understand it. Most people go through life accumulating facts, memorizing procedures, passing examinations, and they assume this constitutes knowledge. But real understanding is something entirely different. It's not about what you can recite, it's about what you can do with what you know, how deeply you can explain it, whether you can take an idea apart and rebuild it from scratch, using only fundamental principles. I've spent my career studying how nature works, and in doing so, I've discovered something about how understanding itself works. There are levels to it, distinct stages that you must pass through if you want to genuinely comprehend anything, whether it's physics, mathematics, or any complex domain of knowledge. The first level is the most basic, and it's where most people stop without realizing they've barely started. This is the level of familiarity. You encounter a concept, you hear the words, you recognize them when they appear again. Someone mentions quantum mechanics, and you nod because you've heard that phrase before. Someone writes an equation on a blackboard, and it looks familiar. You've seen those symbols. This feeling of recognition creates an illusion of understanding. Your brain registers familiarity and interprets it as comprehension. But familiarity means almost nothing. A parrot can become familiar with sounds without understanding language. You can be familiar with chess pieces without knowing how to play chess. Familiarity is merely the starting point, yet countless people mistake it for the destination. Watch what happens when you probe someone who has only reached this first level. Ask them to explain the concept in their own words, and they'll repeat the definition they memorized. Ask them why it works that way, and they'll tell you that's just how it is. Ask them to apply it to a new situation, and they'll be lost. They have labels without content, words without meaning. They've learned to recognize patterns on a page without understanding what those patterns represent in reality. The second level is comprehension of definitions. Here, you move beyond mere recognition. You actually understand what the words mean. If someone defines energy as the capacity to do work, you know what capacity means, what work means in the physical sense, and how these concepts relate. This sounds trivial, but it's not. Most technical definitions contain multiple layers of meaning, and you cannot understand the definition until you understand every component within it. Take the definition of electric field, the force per unit charge. You must know what force is, what charge is, what per unit means mathematically, and why we define things this way. Without this foundation, the definition is just a string of words. Many students progress through years of education without ever truly reaching this second level. They memorize definitions for examinations without unpacking what the definitions actually say. They learn that entropy is a measure of disorder without ever asking what measure means, what disorder means in a thermodynamic sense, or why this particular quantity matters. They accumulate definitions like items in a warehouse, neatly labeled but never opened or examined. The third level is where real understanding begins to emerge. This is the level of basic application. You can take a concept and use it in the specific context where it was taught. If you learned F equals man in the context of a block sliding on a table, you can solve other problems about blocks sliding on tables. If you learned the ideal gas law with examples of pistons and cylinders, you can handle similar piston and cylinder problems. You're no longer just repeating definitions, you're manipulating them according to rules you've learned. But notice the limitation here. Your understanding is context-bound. You can apply the concept within the boundaries of familiar examples, but you cannot extend it beyond those boundaries. This is because you haven't yet grasped the deep structure of the idea. You know the surface rules, the procedures, the algorithmic steps. You don't yet see why these rules work or what fundamental principles they express. You're like someone who can follow a recipe but doesn't understand cooking, who can execute the steps but cannot adapt when circumstances change. Most education systems are designed to bring students to this third level and no further. Textbooks present concepts with worked examples. Students practice similar problems. Examinations test whether students can execute these practice procedures. Everyone declares success, and the students graduate believing they understand the subject. But they don't. Not really. They've learned to perform certain operations in certain contexts. That's useful, certainly more useful than mere familiarity or definition memorization. But it's not deep understanding. The fourth level is synthesis across contexts. Here you begin to see connections. You realize that the same concept appears in different areas, wearing different disguises. You notice that conservation of energy in mechanics is fundamentally the same idea as Kirchhoff's voltage law in circuits. You see that the mathematics of a spring and mass system is identical to the mathematics of an LC circuit. These aren't separate facts to memorize. They're the same structure appearing in different physical situations. When you reach this level, your knowledge becomes more powerful because you're no longer learning isolated pieces. You're learning patterns that repeat, principles that generalize. This is where understanding starts to feel different internally. Instead of your head being filled with disconnected facts, you begin to sense an underlying unity. Concepts that seemed separate reveal themselves as aspects of something deeper. Your knowledge becomes compressed, more efficient. Instead of remembering 100 specific cases, you remember a few general principles and derive the specific cases as needed. But reaching the fourth level requires something most people find uncomfortable. It requires that you actively look for connections, that you question why different subjects seem to use similar mathematics, that you don't take coincidences at face value. When you notice that the differential equation for a damped harmonic oscillator looks like the equation for an RLC circuit, you must ask why. Is this just mathematical accident? Or is there a deeper physical reason? Following these questions takes effort. It's easier to learn each topic separately and never wonder about the connections. But if you do the harder work, you discover that nature has structure, that seemingly different phenomena obey the same fundamental laws. The fifth level is where most people who achieve genuine expertise operate. This is the level of first principles reconstruction. At this stage, you don't just use concepts, you can derive them from more fundamental starting points. You can take apart any result in your field and rebuild it from basic axioms. If someone asks you why light refracts when entering water, you don't cite Snell's law as an answer. You derive Snell's law from the principle that light travels the path that minimizes transit time, which itself follows from the wave nature of light and the boundary conditions at an interface. You see the entire chain of reasoning from fundamentals to specific results. This level requires that you've spent considerable time working with ideas, not just reading about them but actively wrestling with them. You've derived the equations yourself, not once but multiple times until the derivation becomes natural. You've worked through the logic carefully enough that you know which steps are crucial and which are just mathematical convenience. You understand the assumptions embedded in every result, so you know when those results apply and when they don't. What's remarkable about reaching this level is that your understanding becomes robust. If you forget a formula, you can rederive it. If you encounter a variation you've never seen, you can work it out from principles. Your knowledge doesn't depend on memory anymore. It depends on understanding the logical structure well enough that you can reconstruct whatever you need. This is what it means to truly know something. But even this isn't the deepest level of understanding. The sixth level is explanatory mastery. Here you can explain concepts to anyone at any level of technical sophistication, making the ideas clear without sacrificing accuracy. This is far harder than it sounds. When you deeply understand something, it becomes obvious to you. You forget what it's like not to know it. The inferential steps that seem trivial to you are enormous leaps to someone learning for the first time. Achieving explanatory mastery means you've reconstructed the novice perspective. You remember what's confusing about the topic, and you can guide someone through the confusion to clarity. I've found that you cannot truly explain something well unless you understand it at the fifth level, from first principles. If your own understanding is superficial, your explanations will be superficial. You'll resort to analogies that don't quite work, to hand-waving over the difficult parts, to asserting things that should be derived. But when you genuinely understand something deeply, you can explain it simply, not by dumbing it down, but by finding the clearest path through the logical structure. There quotes a method I use to test whether I've reached this sixth level with any concept. I imagine explaining it to someone with no technical background, perhaps a bright child or a curious friend from a different field. Can I make them understand the core idea without lying to them, without using false analogies, without telling them to just accept certain things? If I can, then I know I understand it. If I can't, if I find myself saying things like just think of it this way, or it's like this but not really, then I know my understanding has gaps. Those gaps might not matter for using the concept, but they matter for truly knowing it. The process of achieving explanatory mastery often reveals flaws in your own understanding. When you try to explain something and realize you can't do it clearly, you've discovered something you don't actually understand as well as you thought. This is valuable. It shows you where to focus your learning. Many people avoid trying to explain things because they find it frustrating, but that frustration is a signal. It's pointing at the boundaries of your understanding. Now we arrive at the seventh and deepest level, and this is where very few people operate, even among experts. This is the level of creative extension. At this stage, you understand a domain so thoroughly that you can extend it into new territory. You can take the principles and apply them to situations no one has considered before. You can see what questions haven't been asked yet, what assumptions might be relaxed, what new connections might exist. You're no longer learning what others discovered. You're discovering new things yourself. This level requires everything from the previous levels. You must know the definitions precisely, apply them fluently, see their connections, reconstruct them from fundamentals, and explain them clearly. But it requires something more, a kind of intellectual courage and creativity. You must be willing to question things that everyone else accepts. You must be able to hold multiple incompatible ideas in your head simultaneously, and ask what happens if we change this assumption. You must develop intuition about what directions are promising, and what directions are dead ends. What does this progression look like in practice? Let me trace it through a specific example, understanding why the sky is blue. At the first level, familiarity. You've heard that the sky is blue because of something to do with the atmosphere. You recognize this as a physics question. At the second level, comprehension of definitions. You know that light is electromagnetic radiation, that different colors correspond to different wavelengths, that the atmosphere is a mixture of gases. You understand what these terms mean. At the third level, basic application, you've learned about Rayleigh scattering. You know that short wavelengths scatter more than long wavelengths, by a factor that goes as 1 over wavelength to the 4th power. You can calculate that blue light with wavelength around 450 nanometers scatters about 4 times more effectively than red light at 650 nanometers. You can apply this formula to similar scattering problems. At the fourth level, synthesis across contexts, you realize that Rayleigh scattering is related to other scattering phenomena. You see connections to why sunsets are red, the same principle in reverse. Why clouds are white, scattering by larger particles follows different rules. Why the ocean appears blue, combination of scattering and absorption. You notice that scattering appears throughout physics. Photons scattering off electrons, neutrons scattering off nuclei, sound waves scattering off obstacles. The mathematics has common features. At the fifth level, first principles reconstruction, you can derive Rayleigh scattering from Maxwell's equations. You start with an electromagnetic wave encountering a molecule. The oscillating electric field induces an oscillating dipole moment in the molecule. This oscillating dipole radiates, and the radiated power depends on the 4th power of frequency, which translates to inverse 4th power of wavelength. You understand every step of this derivation. You know what approximations you're making, when they're valid, and what happens when they break down. At the 6th level, explanatory mastery, you can explain to a non-physicist why the sky is blue in a way that's both accurate and comprehensible. You might say, light is a wave, and when it encounters something small like air molecules, it bounces off in random directions. This bouncing happens more easily for short waves than long waves. Much more easily. Blue light has shorter waves than red light, so it bounces around the sky much more. When you look at the sky, you're seeing all this bounced blue light coming at you from every direction. That's why the sky looks blue. This explanation is simple, but it's not wrong. It captures the essential physics without requiring technical knowledge. At the 7th level, creative extension, you start asking questions that lead to new understanding. Why does Rayleigh scattering have that specific wavelength dependence? Can we derive it from more fundamental considerations? What happens if the scattering particles aren't much smaller than the wavelength? This leads you toward scattering theory. What if the atmosphere had a different composition? What if molecules had different polarizabilities? You start exploring parameter space, seeing what's universal and what depends on specific details. You might discover something no one noticed before. This progression isn't something that happens automatically. You don't simply absorb information and gradually level up. Each transition requires active effort and specific kinds of practice. Moving from familiarity to definition comprehension requires that you slow down and actually think about what words mean. When you encounter a technical term, don't just file it away, unpack it, break it into components. Make sure you understand each piece. Moving from definition comprehension to basic application requires practice, but not mindless practice. You must work through problems while paying attention to what you're doing. Don't just follow procedures mechanically. After solving a problem, ask yourself what principle you used, why the method worked, What would change if the problem were different? This active reflection converts practice into understanding. Moving from basic application to synthesis across contexts requires a different kind of effort. You must actively look for patterns. When you learn something new, ask yourself where you've seen similar ideas before. Keep a mental or written catalog of recurring structures. When you notice that two different areas use the same mathematics, don't dismiss it as coincidence. Investigate why. What's the underlying commonality? This habit of seeking connections is what builds the synthetic level of understanding. Moving from synthesis to first principles, reconstruction requires perhaps the most demanding work. You must derive things yourself, repeatedly. Don't just read a derivation and think you understand it. Close the book and reproduce it. When you get stuck, and you will get stuck, resist the urge to immediately look back. Struggle with it. Try different approaches. When you finally work through it, you'll understand it far more deeply than if you had just read it. Do this not once, but many times, until the derivation becomes second nature. Moving from first principles reconstruction to explanatory mastery requires that you actually try to explain things to people. Find someone who doesn't know the topic and attempt to teach them. Pay attention to where they get confused. Notice what analogies work and what analogies fail. Refine your explanations based on this feedback. This process forces you to see the material from a fresh perspective and reveals gaps in your understanding you didn't know existed. Moving from explanatory mastery to creative extension is the most difficult transition, and there's no guaranteed method for achieving it. It requires that you've internalized the material so thoroughly that you can play with ideas freely. You need to develop intuition about what questions are interesting, what directions are promising, what assumptions might be worth challenging. This comes partly from experience, from spending enough time with ideas that you develop a feel for them. But it also requires a certain intellectual disposition, curiosity about unexplored territory, willingness to pursue ideas that might not work, comfort with confusion and uncertainty. Now here's something crucial that people often miss about this progression. You don't move through these levels once for an entire field. You move through them separately for each concept within the field. You might have seventh-level understanding of one topic, while remaining at the third level for another topic in the same domain. This is normal. Deep understanding is built concept by concept, not all at once. What matters is that you recognize which level you're at for any given concept and deliberately work to move deeper. Most people plateau at the third level, basic application, because that's where conventional education stops pushing them. They can solve standard problems, pass examinations, and get degrees while never reaching genuine understanding. This is a tragedy because the real intellectual rewards, the deep satisfaction of truly knowing something, only begin at the higher levels. There's another crucial point about this progression. Moving through these levels doesn't just give you more knowledge. It changes how you think. At the lower levels, your thinking is rigid, bound by rules and procedures you've memorized. At the higher levels, your thinking becomes fluid. You can approach problems from multiple angles. You can recognize when standard methods won't work and improvise new approaches. You develop what might be called physical intuition, though it applies to any domain, a sense of what's important and what isn't, what's likely to work and what isn't, what questions are worth asking. This intuition isn't mystical. It's the accumulated pattern recognition that comes from deep engagement with a domain. When you've worked through hundreds of problems from first principles, when you've seen the same structures appear in different contexts, when you've explained concepts dozens of times and seen what confuses people, you build an internal model of the domain that guides your thinking, even when you're not consciously reasoning through every step. The question people often ask is, how long does this take? There's no single answer because it depends on the complexity of the domain, the quality of your practice, and your starting point. But I can say this: reaching the higher levels for any substantial concept requires sustained effort over months or years, not hours or days. Deep understanding cannot be rushed. It must be built carefully, layer by layer, with each layer solid before you build the next. This is why cramming doesn't work for genuine learning. You might be able to cram enough facts into short-term memory to pass an examination, reaching the second or maybe third level temporarily. But real understanding, the kind that persists and grows over time, requires that you work with ideas repeatedly, approaching them from different angles, connecting them to other ideas, using them in varied contexts. This takes time. People sometimes find this discouraging. They want to learn quickly, to master things efficiently. But there's no shortcut to deep understanding. The 7 levels represent real cognitive development that must happen in your brain. Neural connections must be formed and strengthened. Pattern recognition systems must be built through experience. This is biological reality, not a pedagogical choice. However, understanding this progression is itself valuable because it lets you direct your effort effectively instead of passively consuming information and hoping understanding will emerge. You can actively work at the appropriate level. If you're at the definition comprehension stage for a concept, don't pretend you're ready for creative extension. Focus on the next step, basic application, work problems, see the concept in action, then move to synthesis, then first principles, and so on. What I've described here isn't just about learning physics or mathematics. This progression applies to any complex domain: music, chess, writing, engineering, medicine. The specifics differ, but the underlying structure is the same. True mastery requires moving through these levels of understanding, and there's no way to skip levels successfully. The deepest insight from recognizing these levels is this: most of what passes for knowledge in the world is actually familiarity, or at best, basic application. Most people who think they understand things actually don't, not deeply. They know enough to get by, to sound informed in conversations, to handle routine situations, but they haven't done the work required for genuine understanding. This isn't a criticism. Deep understanding is difficult and time-consuming. For most topics in life, basic application is sufficient. You don't need seventh-level understanding of how your car works to drive it competently. But for the things that matter to you, for your primary intellectual pursuits, for the domains where you want real expertise, settling for superficial understanding is a waste of your potential. The 7 levels are a map of the territory between ignorance and mastery. Knowing the map doesn't automatically get you to the destination, but it shows you where you are and what comes next. And that knowledge, applied with discipline and curiosity, is what transforms someone who merely knows about things into someone who genuinely understands them. That transformation from surface familiarity to deep comprehension is what real learning looks like. Everything else is just preparation or pretense.